Kenny Jones is a fourth-year CS PhD from Brown University, advised by Professor Daniel Ricci, and he is broadly interested in machine learning AI techniques to better understand and represent 3D data. So recently, he's been working on combine explicit symbolic representations, for example, programs, and neural method in order to generate, analyze, and edit 3D shapes.
Thanks for the great introduction for having me at the workshop. It's a pleasure to be here. So today I'll be talking about some work on 3D shape analysis over region decompositions. And this is probably not news for this audience, but 3D shapes have structure. We often want to figure out how to parse the structure in a way that's useful for different downstream applications. So given a 3D shape, there are many things we might want to understand about it. For instance, we might want to segment it into semantic parts. We might want to know different motion paths that parts in a shape can take, or we might want to be able to find an editable and interpretable representation of a 3D shape, for instance, in the form of a visual program. So in this talk, I'll be discussing approaches for 3D shape analysis that operate within a two-step paradigm. So first, a shape is going to be decomposed into regions, and then these regions are going to be provided as input for a shape analysis method. So instead of end-to-end learning over the atomic elements of 3D shapes, like points in a point cloud, the methods in the second step instead search over shape regions. So why might we want to do this? Well, if you're successful in the first step and you find a useful region decomposition, it greatly simplifies the second step as the size of the search space gets greatly reduced. And having access to this tractable, discretized state space is much more compatible with a wider range of search algorithms beyond just gradient-based optimization. So how do we actually get useful region decompositions? So this is a core problem at the heart of computer graphics and vision, and many families of approaches have studied it. So traditionally, right, this would be done in kind of non-learning based frameworks that would leverage geometric properties of input shapes. More recently, with kind of the takeover of learning-based systems, a popular approach is to use end-to-end networks that globally learn part decompositions when annotations for the task and category of interest are available. And an alternative, increasingly popular strategy is to instead employ a learning-based method that attempts to represent a 3D shape as a collection of simple primitives, for instance, cuboids or convexes, or even more general local neural networks. And these approaches are great because they can train in unsupervised fashion, avoiding the requirements of fine-grained label annotations, but their reconstruction-based objectives are often prone to missing fine-grained parts, and finding good solutions in this spaces often requires complicated regularization terms during the objective optimization. So instead, I want to talk a bit about a different approach that our group has developed for this problem called SHRED that we presented at last year's SIGGRAPH Asia. And the main motivation of this method is that there are some domains of 3D shapes that have abundant fine-grained annotations in data sets like PartNet, for instance, lamps and chairs, while other categories of shapes have much less fine-grained annotations available, like earphones and faucets. And in SHRED, our idea is that we want to learn over in-domain shapes from these data-abundant categories, and then find policies that generalize out of the box to shapes from these out-domain categories. So how do we actually learn a policy that generalizes in this way? The intuition we had is that while reasoning over global part segmentation is really domain-specific, the local part segmentation task actually looks very similar across different domains. So in SHRED, we learn these three shape decomposition operations that are only allowed to reason locally. So we have a split operation that learns a network that breaks a region into subregions. We have a fix operation that learns a network that, conditioned on a local region, better aligns and fixes its boundaries with neighboring regions. And then we also have this merge operation, which learns a network that considers neighboring regions to decide if they should be combined or be kept as separate parts. And so we find that SHRED's locally learned operators, when they're trained on these data-abundant in-domain categories of shapes, learn to produce region decompositions that well match fine-grained part instance segmentations, outperforming alternative approaches with respect to AIOU on test set shapes from in-domain categories. But perhaps more interestingly, we also find that SHRED's policies, because of this local bias, just generalize out of the box much better to kind of shapes from out-domain categories over comparison methods in just kind of this zero-shot transfer learning type paradigm. So jumping back to the big picture, once you actually have shape regions, what can you actually use them for? So take a task like semantic segmentation. When you have shape regions, the goal is no longer to label the atoms of the shape. So for instance, like points in a point cloud, but rather to give a semantic label to each of the regions. So we've actually developed an approach within this paradigm named NGSP, the neurally guided shape parser, which we presented at CVPR last year. And NGSP uses two types of learned modules. So one module, the guide network, learns a neural prior over likely semantic labels for each of the shape regions in isolation. And we can treat this guide network as kind of a local approximation of the posterior and use it to import and sample a large number of possible label assignments to the input shape. Then we can have another set of learned modules to form a likelihood function where different subcomponents reason over either properties of the semantic labels of the grammar or properties of groups of regions implied by a given label assignment. We can then take each of the proposals from the guide network, evaluate them under this learned likelihood, and then select the highest probability assignment within the set as kind of the output segmentation. So if we want to run NGSP over input shapes, we can first find a region decomposition using a method like shred, and then we can use NGSP to find a high likelihood label assignment over the shred created regions. And comparing the predicted semantic segmentations to human annotations, we found that this two-step approach creates much improved predictions over using end-to-end networks that don't use shape regions, but instead try to find fine-grained semantic segmentations over shape atoms directly. And I also just wanted to mention this related work, COW3D, from some folks at SFU, which is a really great system that proposes a labeling interface using hierarchical reasoning and active learning to create human quality fine-grained part annotations, like those found in PartNet, with much less human annotation time. And kind of critically, just like NGSP, they search over shapes that have been already decomposed into regions, which greatly constrains and makes tractable this really hard search problem. So switching gears a bit to another shape analysis task, we've also investigated how region decomposed shapes can be used to improve visual program inference. So we developed a method, ShapeCoder, which we'll be presenting at SIGGRAPH this year, that takes in an input data set of shapes represented with primitives. And then it automatically discovers a library of abstraction functions, and then also infers visual programs that use these abstractions to compactly explain shapes from the input data set. So these discovered abstractions capture common patterns, both structural and parametric, so that programs rewritten with these abstractions are more compact and expose fewer degrees of freedom. So for instance, the orange and purple abstraction shown here can be broadly applied across different input tables to explain the same structural concepts, even if those components are expressed with diverse geometry. And moreover, having access to this programmatic representation with abstractions supports downstream applications like shape editing directly, as the parameters of the inferred program can be modified to explore a family of related shapes. And once again, to solve this hard problem, that of finding a library of abstractions and programs that use those abstractions that's specifically tailored for a given data set of complex 3D shapes is only made tractable because we assume that each of these shapes is decomposed into primitive approximated regions. So now that we've talked about some different approaches for 3D shape analysis within this paradigm, I wanted to offer some thoughts on interesting future directions. So as I've mentioned a couple of times, performing shape analysis over shape regions provides an opportunity to employ more powerful search algorithms. And while some work has been done along this direction, I think pushing this line of investigation further is a really great direction. So one recent example here that I really liked is this split, merge, and refine work out of KAIS, where starting with shape regions produced by BSPNet, they employ a Monte Carlo tree search along with some continuous optimization in order to find a set of tight-fitting bounding boxes for a 3D shape. Another benefit of operating within this kind of two-step paradigm is that a broader class of objective terms can be employed, as unlike end-to-end systems, not all of the terms need to be made differentiable into loss functions. So we explored this a bit in NGSP, where we learn a likelihood function that we run discrete search over. But I think this paradigm opens up even more extreme possibilities, where, for instance, part-to-part relationship rules influence the likelihood function. And as a motivating example for why we might want to do this, human labelers of data sets like PartNet were given both rules and examples for how parts should relate to one another. For instance, in the definition of a back frame, it should outline a back surface part. And I think there are opportunities within this paradigm to give the same kind of information to shape analysis methods. And finally, I also just want to note that the task of finding a good region decomposition is far from being solved. In fact, you might argue that the exact type of regions you might want could differ depending on the downstream task you're working with. So an interesting question here is whether region decomposition methods can be made aware of these different downstream requirements. So for instance, in Shred, we apply these local operations in a fixed order to produce decompositions. but maybe a meta operation scheduler could be employed to apply additional operations based on feedback from the shape analysis method itself. So as one example, if a semantic labeling method identifies under segmentation in a region, the shred split operation could be called to further decompose it. And as a closing meta comment, I think really successful methods within this paradigm will need to have kind of an open loop communication between how regions are produced or modified and how those regions aid search for the downstream shape analysis task. And yeah, thank you so much for listening, for having me. Thanks also to my great collaborators at Brown, Adobe, UCL, and Chicago. All the papers, project pages, and code for the approach I talked about can be found on my website. And please feel free to reach out afterwards with any questions. Thanks.
Cool. Thank you.